This lecture introduces the row space and the column space of a matrix. First, let's talk about the definitions of the row space and the column space. If we let A be an m by n matrix, then the row space of A is defined as a subspace of R1 by n, spanned by the row vectors of A. A row space is a span of row vectors of A. Okay. And similarly, the column space is a subspace of Rm and is spanned by the column vectors of A. So let's look at an example. You have A is a 2 by 3 vector, a 2 by 3 matrix. You want to define the row space and the column space of A. So first, the row space of A, usually we know about using RA, is a span of the set of row vectors of A. So the first row vector is 1, 0, 2. And second row vector is 0, 1, 0. Okay. Again, the span of a set of vectors is all the linear combinations of these two vectors. About the column space of A. Usually we denote it using C of A, is a span of column vectors of A. So the first column vector of A is 0, 1. Second column vector is 0, 1, 0, 1. And the third column vector is 2, 0. Okay. Well, if we look at this matrix here, you can see that this is the row echelon form. The first and the second columns are pivot columns. And the third columns is the free, if you look at a system is a free variable. So you can see that the third column vector depends on the first and the second vectors. More specifically, C3 is in this case E2 times C1. So this is the relation between C3 and C1. Now, C1 and C2 are independent. C3 is a linear combination of C1 and C2. Thus, if you want to reduce this set of vectors, you can just reduce this to the first and the second column vector, because the third one is just a linear combinations of the first and the second vectors. All right. Now the first theorem in this section is saying that two row equivalent matrices have the same row space. Okay, so you have matrix A, all right, and then you do some row operations. You get to matrix B. And when you are doing row operations, actually you're just finding different linear combinations of some rows in A to define some rows in B. So keep in mind, row operations are, you have like, let's see, row 1 swap to row 2, right? Or row 2 is row 2 times 3, for example, or row 3 is the same as row 1 plus 2 row 2, right? These three row operations here are forming linear combinations of some rows in A to produce rows in B. So that's why they are just sharing the same row space. If they are row equivalent matrices, they have the same row space. Well, the next definition is the rank of A. So the rank of A is defined, first is denoted using rank A, and is defined by the dimensions of the row space of A. So the dimension is the minimum number of vectors that can span the entire row space of A. If we look at this example here, so the row space are spanned by two independent vectors. So that means the dimensions of the row space of A should be 2. And since the dimension of the row space of A is 2, that means the rank of A is also 2. Okay. The next theorem is the rank Nulli theorem. So if you have an n by n matrix, then the rank of A plus the nullity, which is the dimension of the null space of A, equals to n, which is the number of column vectors. Okay, again, the rank of A, by the definitions, is the dimensions of a row space of A, plus the dimension of the null space will give you the number of column vectors. All right. The last theorem in this section is if you have an n by n matrix, the dimensions of the row space of A is the same as the dimensions of the column vectors, column space of A. So the dimensions of the row space is the same as the dimension of the column vectors, column space of A. So if we look at this first example here, we know that the dimension of the row space is 2 because it has two independent vectors. Also, when we look at the column space of A, at first we had 3 vectors, but we found that the third vector is a linear combination of the second and the first and the second vectors. So that's why we reduce the number of vectors in this column space from 3 to 2. And as we know that the dimensions of the column space is just 2 because you only need 2 vectors to span the whole entire column space. So in this example, you can see that it matches to the theorem of saying the dimension of the row space is the same as the dimensions of the column space, and it's equals to the rank of A. Okay, well, let's look at the next example. If you have a matrix B, okay, and then here I found the row echelon form of B, which is U, right? U is a row echelon form of B. So I just reduce B down to a simpler matrix. So if you look at these two matrices and you want to find the rank of B, okay? So the rank of B is the same as the dimensions of the row space of B, okay? And since B and U are row equivalents, then they have the same dimensions of the row space and they share the same row space, which is, and then if you look at matrix U, the row space of U is spanned by 2 vectors. This is the first row vectors and this is the second row vector. So that means the dimensions of U of the row space of U equals 2, and which is the same as the dimensions of the row space of B, which is equals to the rank of B. And as we found that the dimensions of the rank of B should be 2. And what is the dimensions of the null space of B? So we use the rank nullity theorem. We say, we know that the dimension of the row space of a matrix plus the dimension of the null space equals the number of column vectors. So we say the dimensions of the row space of B plus the dimensions of the null space of B equals to 4, which we have 4 columns. And we know the dimensions of the row space of B is 2, that we found it up here, plus the dimension of the null space, and we can call it the nullity of B equals to 4. That means the nullity of B equals to 4 minus 2, which is 2. All right, now we're going to find the dimensions of the null space of B transpose. So if we observe B and B transpose, right, we know that the dimensions of B, of the row space of B, should be the same as the dimensions of the column space of B transpose. Because when you transpose, you just interchange row and column. And the dimension of the column space of B transpose, it should be equals to the rank of the B transpose. Well, you can use the, and the rank is equals to the dimensions of the row space. Now we can use the rank nullity theorem. We know that the rank, the dimensions of RBT plus the dimensions of the null space, the nullity of B transpose, equals to the number of columns, right? And the number of columns of B transpose is the number of row of B, which is 4. So that's why the nullity of B transpose equals to 4 minus the dimensions of the row space of B, which is just 2. So in this case, the dimensions of the null space of B transpose is also 2. Now we can talk a little bit about the column space. Well, in the previous example, B and U are row equivalents. More specifically, U is the row echelon form of B, right? And we know that they are not sharing the same column space. So the column space of B is not the same as the column space of U. We know that. But the relation among the column vectors of U is the same as the relations among the column vectors of B. So let's say this is U1, U2, U3, U4. This is B1, B2, B3, and B4, okay? If I look at U1 and U2, U1 and U2 are the 2 pivot columns. That means U1 and U2 are independent, and U3 and U4 depending on U1 and U2. More specifically, U3 and U4 are linear combinations of U1 and U2. So let's say U3, you see clearly that U3 just 2 times U1 plus 0 U2, right? How about U4? U4 is going to be something about 2 times U2, but 2 times U2 is 4, and it should minus 1 to get 3, so it's negative U1 here, plus 2 U2. Okay. Well, if you know this relations among U1, U2, U3, and U4, then you can conclude about the relations among B1, B2, B3, and B4. So and say the same, B1 and B2 are linearly independent. B3 equals to 2B1 plus 0B2, and B4 equals to negative B1 plus 2B2. All right. So that's something that we notice about the relationship between B and U and column vectors in U and column vectors in B. Okay. Now the row echelon form tells us only which columns of A to use to form a basis. So for example, if you look at U as the row echelon form of B, you know that U1 and U2 are linearly independent, and they can form a basis of the column space of U. And also B1 and B2 are linearly independent, so they will form a basis for the column space of B. So look at this, the first two columns vectors of B forms a basis for the column space of A because they are independent. And the third and the fourth column vectors are just linear combinations of B1 and B2. That means we can take them out from the basis, right? So the basis only contains two vectors. Well, let's look at the next example here. If you have a matrix 4 by 4, right? And this matrix A here is already reduced to the reduced row echelon form. So this matrix is the reduced row echelon form of A. Now, if you given that A1 is this vector, A2 is this vector, can you find A3 and A4 given the reduced row echelon form of A? Again, we can use this reduced row echelon form to find the relations among column vectors of A. Again, the first and the second columns are independent. Well, the third column will be, you see that is 2 times A1 plus A2. And the fourth column is going to be just A1 plus 4A2. Okay, A1 plus 4A2. So now we know that A1 and A2, we can find A3. So A3 again equals to 2A1. A1 is negative 3, 5, 2, 1. Plus A2, which is 4, negative 3, 7, negative 1. And A4 is going to be A1, which is negative 3, 5, 2, 1. And plus 4 times 2, 4, negative 3, 7, and negative 1. And we just do these two calculations to find A3 and A4. So this should be negative 6 plus 4 is 2, 10 minus 3 is 7, 4 plus 7 is 11, and 2 minus 1 is 1. And this is going to be negative 3 plus 16 is 13, 5, negative 12 is 7, 2, 28, 30, and 1, negative 4 is going to be negative 3. So we just found A3 and A4 using the information of A1 and A2 and using the information of the reduced row echelon form of A. Okay. Now we're going to look at how row space and column space related in linear systems. So the question is, how do we determine the solution set of a linear system utilizing knowledge of the vectors independency, column spaces, and basis of vector spaces, etc. So that's the questions. Well, to answer the questions, we can talk about the theorem, consistency theorem for linear system. Okay, so if you given a linear system AX equals to B, and this system is consistent, which means it has at least one solution, if and only if B is in the column space of A. Okay, so if B is in the column space of A, that means B is a linear combination of column vectors of A. Okay. So if B is a linear combination of column vectors of A, that means the system AX equals to B has at least one variable. Okay. And the next thing is if B is 0, then you have a homogeneous system. And the system will have only trivial solutions if and only if the column vectors of A are all linearly independent. So if you have a homogeneous system equals to 0, then this system will have only trivial solutions if and only if the column vectors of A are linearly independent. If and only if, right, column vectors of A are linearly independent. What does it mean? That means if all the column vectors of A are linearly independent, that means you don't have any free variable. All the column vectors are representing for lead variables. So if you don't have any free variables and the homogeneous system is always consistent, that means the only solution that you will have, it will be just the trivial solutions. Again, so the system, a non-homogeneous system, is consistent if B is in the column space of A, and a homogeneous system AX equal to 0 has only trivial solutions if all the column vectors of A are linearly independent. But the next theorems is if you have a matrix n by n matrix, right, and then you consider the system non-homogeneous system AX equals 0, and this system is consistent for every vector B in Rm if and only if the column vectors of A span Rm. So if the column vectors of A span Rm, that means any vector in Rm will be a linear combinations of Rm, right? And if that means B is a linear combinations of column vectors of A, so that means AX equals to B will be consistent. That's how we visualize, that's how we rationalize this theorem. So let's say column vectors of A span M. Rm means B in Rm is a linear combinations of column vectors of A. That would tells you that if B is a linear combinations of column vectors of A, that tell you that AX equals to B has at least one solutions. Thus is consistent. And is this if and only if, that means if this system is consistent for all vector B in Rm, then all the column vectors of A are linearly independent, or all the column vectors of A span Rm. Well, the second statement is the system, non-homogeneous system, has at most one solution for every vector of B in Rm if and only if the column vectors of A are linearly independent. So the first statement tells you that if the column vectors of A span Rm, then the system is consistent, has at least one solution, and reduced to the system to have at most one solution. If for every single vectors of B in Rm, the column vectors of A are linearly independent. So all the column vectors of A are linearly independent, then this system here only has one solution. All right, so this is the theorem that connects directly from the system, a linear system, and the column space, like column vectors in the matrix A, right? If it's span Rm for all B, then it's consistent. If all the vectors here are linear independent, then it won't have at most one solution. Well, the next theorem, which is the last theorem in this section, is if you have a square matrix, and if this matrix is non-singular, that means an inverse exists, right? If and only if the column vectors form a basis for Rn. Okay, so you can see that it makes sense. If the column vectors form a basis for Rm, that means all the column vectors are linearly independent. And you have n column vectors. And if they are linearly independent, then you will have at most one solutions for the system Ax equals to B. That means you the inverse of A exists. That means A is non-singular. Okay, so you want to use from now on, you learn all these theorems, and if you are about to do a proof problem, you can use the results of all these theorems to show your work. Okay. You want to understand, remember all the definitions of linear combinations, non-singularity, you know, what is a basis, linear independencies. You use all of those concepts and definitions, memorize them, learn how to use them, and learn how to use other theorems in order to do proof problem. All right, here we go. This lecture introduces the row space and the column space of a matrix, and how row space and column space related directly to the linear system of linear equations.